So welcome back to a new lecture. Today we'll be looking at segment anything model. This is a very, very popular model. I'm sure many of you have probably heard of this or at least read about it somewhere on LinkedIn or Twitter or something. So SAM or segment anything model was introduced by Meta, and this is the paper. The paper came out in sometime in 2023. It has almost 16,000 citations. It's a very, very popular paper, and the model has newer versions now. I think there is segment SAM version 3 and other versions coming out, but we'll be discussing about the original legacy version which they introduced through this paper. The paper is also very well written, although it looks a little bit long. The main crux of the paper is just in the first, I think, 10 or 9 pages. So, and that too, most of them are figures. But one thing I realized while reading this paper is that the way they have explained the architecture itself is not extremely beginner friendly. You will have to spend a little bit of time to understand the architecture properly. And we'll anyway do that in today's lecture, but I still recommend you to go through the paper if you have the time. So the first question is, what is segmentation? What is this operation? In the last lecture, we looked at detection, object detection. Before that, in general, we were looking at models that could do classification. And now we are moving into models that can do segmentation. So segmentation is a different type of computer vision related task. So in segmentation, unlike in detection where we are drawing bounding boxes, we won't be drawing bounding boxes, but rather the output will look something like this. This is like a segmentation mask output. And what you can see here is every single pixel is classified into one of the 2 or 3 or how many other classes there are. And they are denoted by these colors. So here you can see that it's not like drawing a bounding rectangle and saying in a vague way, the object of your interest is somewhere inside this rectangle. It's not like that. You need more precision. You need pixel level precision. So of course, segmentation task is a bit more complex than object detection task. There are broadly 2 types of segmentation. One is called instance segmentation and another is called semantic segmentation. In semantic segmentation, it doesn't matter which instance of a specific class your pixel is. So for example, these group of pixels, these group of pixels, these group of pixels, they all belong to the same class called person class. And because of that, they are all given the same color. They are all assigned the same mask. In instance segmentation, these 3 will be in different colors. So their class will still remain the person, but they will be 3 different instances of the same class. So that is called instance segmentation, and this is called semantic segmentation. In segment anything model, it can basically perform anything. It's almost universal. So we'll come to the details of segment anything paper. This is just the initial section of the paper with the basic figure that explains the architecture in a very vague way. I'm not going to go to the detail right now. In a moment, we will do that. The paper is fairly highly cited. It's been just 2 years, slightly more than 2 years, already 16,000 plus citations. I'm pretty sure this paper is going to blow up in the coming years because many other new models will be built on top of SAM. The data set which was used for constructing segment anything model was actually huge. There were roughly 11 million images, and there were around 100. On an average, there were 100 masks per image. That is on an average. Some images have 50 masks, some images have 100 masks. And here I'm talking about training data. So how exactly will the training data look like? You will have an image. Let's say it looks like this. If it was object detection task, your training data would involve ground truth rectangles like this with the coordinates plus whatever is the class inside this rectangle, right? So person. And then you will make predicted boxes. Predicted box may look like this. And then you will compare how the predicted box and the ground truth box look like, how the class, predicted class and ground truth class look like, and you will construct a loss based on that difference. In segmentation, there will be ground truth. The ground truth will look like ground truth mask. For example, this image is a really good example of how a ground truth mask may look like. Ground truth mask will be of similar size as that of the original image. So if this image is 1024 by 1024, you will have an associated binary mask. If you are talking about just one class, you will have a 1024 by 1024 pixel mask, in which those pixels with the class of interest is there. So if you are only interested in person, those pixels will be or black or white. Remaining pixels will be the opposite color. And this segmentation mask will be compared, this ground truth segmentation mask will be compared against the predicted mask. So mask prediction like this is the ultimate goal of the segmentation task. You can overlay the mask on top of your image. So that is what is shown here. So here they are showing the image plus the mask overlay. So you can see there is some mask. I'm sure this is corresponding to some trees. There is some mask corresponding to person. There is some mask corresponding to this person's t-shirt, these trousers, this shoe. So around every object here, you can see masks, right? So you can overlay the mask on top of it. So why is this such a big deal? Why is drawing these masks around people such a big deal? It's because that then you know that the model is really understanding what is going on in the image. Because if you ask a kid to draw an outline around the car, if that much is the instruction that you give to a kid, the kid might be able to draw exactly around the car, right? Just like that, if a deep neural network model can also do the same, it means it really understands the image really well. So that is the big deal about the mask. Mask allows you to hyper localize where your object is in the image. It allows you to have pixel level precision over where your image is and where is your image not. So this image is kind of adopted from the paper figure itself. So this is an example where 50 to 100 masks were there in the image. So the one mask is here, this bounding region, which is bounding the trees. This, you can see another mask with purple color around the person. Here is another mask. Here is another mask. Here you can see another mask, because here the mask is overlaid on top of the image. So in this image, there are roughly 50 to 100 masks. In this image, there are between 100 to 200 masks. There are a lot of vegetables. So maybe they have different masks corresponding to different instances of the same object. There is different mask for this wheel. There is a mask. This wheel, there is a mask. So these two images have 100 to 200 masks per image. I'm just showing you the data set, sample data set that Sam used. We will also discuss how masking is done. That's a very interesting question, because to create these masks in the first place as ground truth is not easy, right? Somebody has to do something to have the masks. We'll discuss about that in a bit. Then this is another image example where there were 200 to 300 masks per image. So on an average, there were around 100 masks per image. Like that, there were 11 million images. So totally, there are 1.1 billion masks in the whole data set that they created. Now, obviously, you know that having a data set with 1.1 billion masks is not something that you have outright available on the internet, right? So, and it's impossible for humans to sit and create these masks manually. You can imagine how humans would have created the ground truth bounding box rectangles. You can simply assign somebody, hey, in all the images, find wherever there are people, draw bounding boxes around them. Then I can just click using my mouse and draw like a bounding box rectangle. I click and drag from one corner to another corner to create the box. So box creation for ground truth making purposes is a bit easy. Mask is not easy. How do I draw? Like if I'm a human annotator, it's not easy. I can do it for maybe 10, 50 images, but how do I do it for 1.1 billion masks? It's nearly impossible. So there was, of course, a deep neural network involved in creating these images in the first place. So we will come to that in a little bit. But the basic idea is this: you have to have the images, and you have to have ground truth masks. Those masks should be associated with object classes. And then you can use this data set for training your model. Okay. That's the basic idea. Almost similar to any other deep neural network training. Now, the task part is what is very interesting in segment anything model. If you look at any other segmentation model like mask RCNN or any other previous models, the way it worked was, let's say you have masks corresponding to two type of objects. Two type of objects, let's say cats and dogs. You might have masks corresponding to cats, you might have masks corresponding to dogs, and you will perform training using that ground truth data on your model. Once it is trained, the model is now able to, in any new image, it's able to identify those objects, cats or dogs, right? This is how it is normally done. But what the researchers who worked on this paper, what they wanted to build was a very general purpose foundational model for segmentation, which is kind of class agnostic, meaning it doesn't matter what I'm trying to segment. If I pick an image and if I click somewhere in the image, I should be able to get a mask around where I have clicked. So if I click on top of a person, I should be able to extract a mask corresponding to that person. If I click on a tree, I should be able to, I should have a model which predicts the mask around the tree by knowing that I have clicked the tree because I need the mask around the tree. So this is called promptable segmentation because a user is giving a prompt in the form of a click. The prompt could also be in the form of a text. Let's say I can type, hey, can you find mask around, or can you find all the objects that are vehicles in this image? Then ideally, I should get a set of masks around all the cars, all the bikes, whatever vehicles there are in the image. So this idea is called promptable segmentation. And that is something that really made segment anything model popular. Now, does it mean that when we are using the model for inference, we give two inputs, we give image as well as some prompt as the input? Yes, that is correct. Usually in any normal segmentation task, we just give image as the input. The output will be the masks corresponding to whatever task this model was trained on. But here user has to give a prompt and there has to be an image also as the input when you are doing inference on the trained segment anything model. Okay, so just remember this word promptable segmentation. We will come to the details of how the prompt is taken into account, etc. Now there are actually four types of prompts this paper discusses. One is point prompts. Point prompts meaning, if let's say this is my input image, there are two cats and like a cup is there. If I click here, that clicking position is a prompt. It has an XY coordinate. Now, why did I click here? Maybe I clicked it because I want to select this cat. Okay. Maybe I clicked here because I want to select both cats. Maybe I clicked here because I want to select only the body of the cat. Maybe I clicked here because I want to select only the face of the cat, right? So my click has some ambiguous meaning. The model has to figure out what that meaning is. So that is, just keep this in your mind. Another type of prompt could be, I could simply draw vaguely a bounding box. So I could draw a bounding box around this cat and say, find a mask around the objects inside this bounding box. Now the model has to figure out, why did I draw bounding box here? Maybe because I'm interested in creating a mask around the cat. If I drew the bounding box like this, the model has to figure out, maybe I'm interested in the cup. Maybe I'm interested in the cat. Maybe I'm interested in both. So this is a vague instruction in the form of a bounding box prompt that I'm giving. The third type of prompt that we can give is just give a vague mask itself as the input. So let's say the vague mask that I'm giving is, I'll just draw some shaded region here. So I'll just say, hey, this is the rough region in which I'm interested to find a mask, like exact mask around the object. So now based on this rough mask that I have provided, the model should guess whether I have asked the model to give out the mask corresponding to the cat or two cats or whatever. The fourth prompt, which the paper discusses, is text-based prompt. Although the model does not directly allow input of text, I will explain how it is still possible in the model. It doesn't allow directly, but it allows indirectly. But we will discuss that. Here, I just want to give you the idea about these prompts. So I could be just typing, hey, I need to find a cat with brown color ears, something like that. And then I should be able to, the model should be able to output the mask around just that particular cat, right? So model should somehow be able to take these different types of prompts into account. This fourth one is an exception. Just keep that in your mind. Mainly these three prompts into account. And model should be able to give me a mask around it. So here, see the mask. That prompt, the text prompt was black cat with ears. That should give me this because this is the black cat with black ears. Then see this mask. This mask is roughly surrounding this cat around this region. So it should give me the cat. Again, see this bounding box. It's also roughly around this region. So it should give me the cat mask. Then again, I have 3 points that I have selected here. So these points should correspond to whatever images that I as a user am interested to click. So I will be giving some ambiguous output. Ambiguous not for the user, but for the model, because when I click something, model does not know whether I'm clicking that particular object or that group of objects. It's not clear. So I will also discuss how the model, how segment anything model takes care of that also. Now, this ambiguous model, here is an example. Let's say I click over here in the image. Maybe I'm clicking just to get this full body of this bird, this emu, or just to get only the body excluding the legs, or just to get the head. The model is not sure why I click just this specific region. Maybe I just want this local mask. Maybe I just want this sub-local mask or global mask. So what the model actually does is it creates 3 levels of masks. So here, if you zoom in, you can see one level is it identifies the whole object. This is like this whole bird object. That is one mask. I hope you can, it's a bit faint, but I hope you can see this red color outline around the whole object. Another mask that it outputs is this mask around just the body of the object. The legs are excluded. Another mask is because I have clicked the head region, it provides a mask just around the head. So basically, for a given prompt or given set of prompts, in one inference or in one forward pass, the model outputs 3 masks. Here is another example. So here, when the green color click dot is here, the model is not sure whether we are asking to identify this whole board or just this Zurich or just the letter Z. So model outputs 3 masks. So this is the mask level 1. Second is mask around this whole word. And third is mask around this letter. And why is the model doing this? Because the clicking as a prompt is a little bit ambiguous. So model gives 3 levels of mask like this to kind of get rid of that ambiguity so that I as a user can pick whichever I intended to pick in the first place. Okay, that is the first thing. So in every inference in one forward pass, the model output 3 masks. Okay. Now, the architecture is seemingly simple. I deliberately use the word seemingly simple because it's not actually that simple, but it's seemingly simple. So let's go through that. First, before I go show you this diagram, let's imagine what are the inputs that we have. We have image is one of the inputs. Okay. Second is I need prompt. Prompt is another input. And third is the output. And what is the output? Can you put in the chat? What is the output that I get from the model? The output is the mask, right? We are trying to get masks out of the model. Now, usually, I mean, we are talking about transformer architecture for vision. So we have to do something to the image, something to the prompt, and somehow we have to create the mask. So just based on logic, okay, what do we require? Do we need an encoder or decoder for converting this image into some sort of embedding? Because we are using transformer to extract features from the image. That extraction can happen through CNN. It can happen through transformer. In various models, we saw the backbone was a CNN. In detection transformer, for example, we were extracting features through CNN. There was no transformer involved at that stage. So here, the image extraction happens through a transformer encoder. Okay, so this is an encoder converts this image into features or feature vectors. The prompt also you need to encode, right? Because prompt is in the form of a point, it is in the form of a box or text, or mask, which we have to convert into some features, right? So obviously here also some encoder might be needed, correct? And this will convert prompt into some, I would say, embedding in some certain dimensional space. Now, mask is the tricky part. Can you guys remember what did we do for detection transformer? In detection transformer, we were trying to predict maximum 100 bounding boxes. How did we arrive at the number 100? The reason why we had 100 bounding boxes was because in a particular part of the model, we had certain number of inputs. What can you remember that? I'm just trying to probe your memory. So in detection transformer, we were converting dash into finally into the bounding boxes. We were converting object queries into bounding boxes, right? We had 100 object queries, and those 100 object queries were converted into maximum of 100 bounding boxes, right? And those object queries we initiated as zeros, and those object queries were passed through what? It was passed through a decoder, correct? So let me show you the diagram. So these object queries, which were initialized, were passed through a decoder, and those same object queries resulted in producing same number of the bounding boxes. Now, by the same logic, if finally we want to predict, let's say, 3 masks, okay, we have to start with some sort of, I don't want to call it as mask query because that is not the term that is used in the paper, but I have to pass something through something. What is this something? I want to finally get 3 masks. What is this? This has to be a decoder, right? And into the decoder, I have to pass something. So I have to pass maybe an initialized version of the masks, right? I also have to pass somehow these two guys because I have image input, I have prompt input, then I have initialized masks. So these 3 things somehow I have to take it to decoder so that decoder can finally produce masks. In detection transformer, we started with input image, which was passed through backbone CNN. Then the image was converted into token sequence. Token sequence was converted to context vectors through transformer encoder. And into the decoder, this input, here we had only one input, which was the image. The transformed input plus the initialized object queries, both were passed into the decoder. Just like that here, we have to pass both of the transformed inputs, which is the image as well as the prompt, plus the initialized mask. So those 3 things we have to pass into the transformer decoder in segment anything model. So, and because of that, we can say there are mainly 3 parts we have to understand in the segment anything model. Part 1 is image encoder, part 2 is prompt encoder, and part 3 is mask decoder. Now here is a question, okay? If we were using, so I did not yet mention whether this encoder and decoder use transformer or not, that we will come to. But if we were using transformer, will we use self-attention or cross-attention? Where will you think cross-attention will appear? Is it in the part 1, part 2, or part 3? Cross-attention will appear only in part 3. Why? Because in part 3 is where tokens coming from different sequences are interacting with each other. Now, part 2, I will come to. I have to spend a little bit of time on part 2, but first I will start with part 1. So just understand this. Decoder is used logically. Think about it. Decoder is used whenever we need interaction, whenever we need to first of all generate something. So you might remember BERT is an encoder only model. GPT is a decoder model. GPT was for generating text. BERT was for understanding text. So if your goal is to just understand an image, you don't want to produce anything, you don't need a decoder. You just need encoder. If you want to produce something, here in this example, you have to produce mask, which means you have to start with something. So that something in the case of detection transformer was object query. So you were starting with object query, and then finally you have to produce the bounding boxes. Then we need a decoder, but that production is dependent on some other information also. What was that information? That information was in the detection transformer case, that information was the input image itself. That input image was converted into features, and that feature, so the way in which your object query was getting converted into final bounding boxes depended on the other stream of input also. Just like that, here, the way in which mask is getting converted, the initialized mask is getting converted. I don't want to use the term initialized mask. I'm just saying that so that you can have an analogous comparison against detection transformer. So the initialized version of the mask can get transformed into the final form of the mask, provided you also have two other inputs, the transformed version of the image and transformed version of the prompt. So decoder is needed whenever you need interaction between two different streams of input, plus you also need to produce something. Okay. Encoder is needed if you only want to learn what is there in that input data. If you just want a good embedding representation, you don't need a decoder, you just need an encoder. And in encoder, typically you will come across self-attention because you have only one stream of data. So within that stream of data, you create attention scores. In decoder, you will typically come across both actually, self-attention as well as cross-attention. Self-attention because here, if you remember from the detection transformer, the first block was a self-attention block where self-attention was constructed between the object queries. Only then cross-attention was created between the transformed object queries and transformed token sequence, which came from the encoder. So now, if I expand the model a little bit, this is how it will look like. There is an input image, and this input image goes through an image encoder, which converts it into image and embedding. Then I have a prompt input. The prompt input is passed through a prompt encoder. So this is the part one. Image encoder is part one. Prompt encoder is part two. That transformed prompt will be passed into mask decoder. One more thing will be the initialized versions of the masks, which may take different form. It will not look like a mask, but we need one more input, right? That will also be passed into the mask and decoder. So mask decoder, which is the part three, will take the image embedding, the transformed prompt, the initial version of the mask, everything together, and somehow it will convert that into final mask output. So mask output may look like a mask around this person or around the trees, depending on the prompt. Now, this looks very simple, right? But there are a few things to note. So firstly, point prompt. So these are the four prompts that we had, right? Point prompt, box prompt, mask prompt, and text prompt. So let's discuss the first three. There is a reason why I put this text prompt in red color. So point prompt is simply an XY coordinate. I can pick n number of points using which I have to make the prediction. But a given point is simply an XY coordinate. It will also have a binary label, whether it's a foreground object or background objects, which can be denoted using 0 or 1. Box prompt also is essentially a collection of 2 points, this corner point and this corner point. So if I have 2 corner points, I have the box fully defined. So I need 2 XY pairs to define a box. Okay. Mask is slightly different. So these two are called sparse prompt. These two are sparse because the input is just this sparse data set, sparse point-wise data set. Mask prompt, which is the rough shape and location of a mask that we are interested in, is called as a dense prompt. Why is it dense? Because here we are having collection of these input points saying that my object may be, it may resemble these collection of dense points somewhat. Here, on the other hand, I'm just giving these two sparsely located points as the input. This is also sparse. I'm just picking these two points as the input. So these are called sparse prompts. These are called dense prompts. Now, mask input, how will it look like? will it look like a collection of points? It will look like a binary mask. So it will look like 1024 by 1024 pixels. If all the pixels are white, wherever the mask is, they can appear black or vice versa, depending on the convention. But this is how the mask will appear. But point prompt and box prompt are easier to represent. It just needs x comma y coordinates. Now, text prompt, although, I mean, when you look at the paper, the figure from the paper, this is how the figure looks like, which shows the model architecture. I just want to show you it once. So this is the figure from the original SAM paper. Okay. And you have input image encoder converted to image embedding. Then the way in which this figure is drawn makes it appear as if SAM directly takes points, boxes, or text as input. And it also makes you think like prompt encoder simply takes points, box, and text. Mask is not an input into the prompt encoder. So there are a few things which may confuse you around this area. So I have my own version of the figure which will make this a bit clearer. Okay. The important thing to notice is that this text prompt cannot be directly taken into the input, but rather what the researchers who worked on SAM did was when they were training, they used clip image embedding also. So clip, you might remember from a few lectures ago, contrastive learning. So you have an image of an apple, a text that is written as apple. This you will pass through an image encoder. This you will pass through a text encoder, and then you will produce vectors. And ideally, these vectors should be aligned. If the model understands the text of an image and text of an apple and image of an apple equally, then the two vectors corresponding to these two embeddings, they should align really well. So this was the whole purpose of the clip model. So what was done during training was they took the object, they converted it into embedding using the clip model, and that was passed into the prompt encoder during the training. Now, the assumption is that if I have access to a trained clip model, into the clip model, it doesn't matter whether I'm passing an image or a text. If it's a trained clip model, both of them will be converted into the same type of embeddings. So indirectly, by training the model on clip embeddings of input images, of training images, you are essentially indirectly also saying I can use clip embedding of input text also, because clip will convert the text as well as image into the same thing, into the same embedding space, right? So, but you cannot, if this clip model or if this clip embedding generator is not available to you, you won't be able to use the segment anything model, at least the first version of the segment anything model with text prompts. So it's not like you can directly enter text. You have to have a clip model in between. The clip model will convert your text prompt into a certain type of embedding, and that embedding you can use to be passed to the prompt encoder. But by default, you can directly pass point prompt, box prompt, and mask prompt. Okay. Now, this is the overall architecture, right? One more thing which I want to discuss is that SAM inferencing is very fast. People have developed applications, like actual applications for image editing using SAM. The reason why that happens is if you look at the SAM model, okay, there is a question. Do we need 4 encoder for prompts? We don't need 4 encoders. Okay, good question. I will come to that. I'm coming to the encoder part. So there are a bunch of things that are confusing regarding this. Do we need different encoder for points, box, text, and mask? Or are these all part of the same encoder and this convolution mask is a different part? So bunch of questions you have, but we are still in the image encoder part. We'll come to the, we are still not into the image encoder part. First, let's go through the image encoder. Then we come to the prompt encoder. So here, the reason why inferencing is so fast in SAM model was because the image encoder is actually not lightweight. This was a vision transformer based model. And this embedding, so converting input image into embedding, was only done once. So during inference, let's say I want to get different type of masks from this input image. I'll pass this image through the part 1 only once. So once I have this embedding, This embedding I can reuse multiple times. So this part might be slow. This image converted to embedding might be a little bit slow because this is a heavy duty vision transformer. But however, the encoder part for prompt and mask decoder are kind of lightweight. Now, the term lightweight is used in the paper only for mask decoder. They haven't explicitly used the term, as far as I remember, they haven't explicitly used the term lightweight for prompt encoder. But I will show you why actually prompt encoder is also very lightweight. So I can input this image into SAM model. I can click here. It will, just segment the sky. If I click here, it will segment the basketball court. If I click here, maybe it will segment the person. If I click here, if it will segment the tree. And each of these clicks are different instances where I am calling the prompt encoder and the mask decoder. I'm not calling the image encoder again and again. Image encoder is used once. Okay, so just remember this SAM inferencing. If you hear from somewhere that SAM inferencing is very fast, this is the reason. The heavyweight part, which is the image encoding part, is done only once. Now, let's discuss, before we go into the architecture, let's discuss briefly how the data set for SAM was created. So they had, in the paper, they described three stages, stage 1, 2, 3. In stage 1, people did manual annotation. They took some data, some images. They created masks manually. So these were basically very high quality pixel level masks. So because human experts are sitting down and creating those masks. So this is a very high quality data, but the quantity of this data is very less because humans can only do so much. So this small data set was initially used to train a version of the SAM, which was like a weak version. It's not highly trained. It's not highly generalizable. Then what they did was they used this weak version of the SAM to produce more masks on more images. So SAM, the first version of the SAM model, will propose masks, and this proposed mask will be based on input point and input box prompt. And then once the model gives you the masks, the humans can either adjust the mask. So if the mask was created in a little bit, slightly inaccurate way, they can adjust the mask rather than entirely redrawing the mask. Then this mask adjustment from a wrong mask to a slightly better mask is faster. They also built a custom user interface for Meta team for building this whole data set. So humans can either refine or add prompts. So let's say it gave a mask around a tree where I actually had clicked a human. Maybe I can adjust the prompt or adjust the mask. And then this corrected versions of mask prompt pair were added back into the training data. So in this process, you will get a slightly better model. Here, humans will start the mask from scratch. Here, humans will not start the mask from scratch. Humans will just make corrections to the mask which was made by the model. In the last stage, they made it highly automated. Highly automated meaning they use millions of images and they produced a lot of corresponding masks, roughly 100 masks per image. Finally, after stage 3, they had 11 million images and 100 masks. So totally around 1.1 billion masks. Humans were not part of this loop, but because of that, some masks will have error. So that is also explicitly mentioned. Some, because the model is making the prediction, humans are not part of the loop. But that error is okay. It will be compensated for by the fact that you have a large data set. So people were happy because data set was so huge, even though human error correction or checking was not there in the stage 3. So this model will produce annotations. This annotation will be adjusted by the human. Once adjusted, it will be added back to the training data. Now this new training data will be used to train the model. So it was like an iterative procedure. So this was called segment anything 1B. The data set was called like that. In the paper, they also discuss a little bit about the balance in the data set, some privacy concerns, etc. So in stage 3, yeah, that's a good question. Is it inference only? There is no training. So whatever is created here, right, will be. So they say, why is this stage 3 images and masks? Why are they helpful? Because it will not have the biases that the humans may have. So when humans are annotating images as part of stage 1, humans may annotate objects that are, let's say, detectable for us, or things that we think are objects. Those things we will annotate as humans. But in stage 3, the kind of objects that the model may be producing along with the human annotated masks will be completely different. And now that whole data set was used for training the entire segment anything model once. So stage 3 was used for producing the data, but this data production was not for creating some public benchmark or anything. It was used for training the SAM model itself. Okay. So the final data set which resulted from this was called SA1B, but that data set itself was the one on top of which segment anything model was trained. All right. Now, so yeah, in the paper, they mention about the human bias. Yeah, stage three is self-generated, but to that self-generated, they will also add the human annotated images as well. So stage 1, stage 2, stage 3, all the images will be added together. And then the whole SAM model will be entirely trained. Then, okay, now let's take a step back. Let's get to the architecture. This is the SAM architecture, right? 3 parts: encoder for image, encoder for prompt, decoder for mask. Now, this may make you feel like the model is simple, but when you actually expand the model actually will look complex. So here I have created a version of my own diagram with part 1, part 2, and part 3 expanded. So now I will not show you this entire image until the very end of today's lecture. I will first pick apart the model part by part. So now let's go into the part 1, which is the image encoder. So now you will hopefully get most of your questions regarding the model answered. So let's start with image encoder. So the image encoder was, as I mentioned, was a vision transformer based model, but it was a pre-trained vision transformer. And the pre-training was done using a masked autoencoder. I will explain in a bit what is this masked autoencoder. We have never discussed masked autoencoder in this course. But the encoder, image encoder, which was used for converting image into input embeddings, was a transformer-based model. The goal here was to convert your high resolution image. So the input image was 1024 by 1024. It will be converted into an embedding of a certain dimension, 64 by 64, but we will look at the exact dimensions, what happens to the number of channels, everything. And this part is what I mentioned. It's a bit inefficient. It's computationally expensive because this is a vision transformer, huge or large model. I forgot, I have to check the paper once. It's vision, VITH or L, and it's only run once during the inference. Now let's zoom in and look at what happens to our image. So you start with the image. The image has 3 channels, 1024 by 1024 pixels along the spatial dimension. Okay, so this is our input. Input image is divided into patches. Patch size is 16 by 16, just like how vision transformer does. And then that means your total number of patches are 1024 divided by 16 along the width, 1024 divided by 16 along the height. So that will be 64 by 64 total. You will have 4096 patches. Now, this is basically a sequence, right? A sequence of tokens where total number of tokens n equal to 4096. What is the dimensionality of each token initially here? The dimensionality of each token is basically one one patch. Each patch is 16 by 16 and they have 3 channels. So the amount of information or the number of pixel wise data that this has will be 16 multiplied by 16 multiplied by 3. So 256 multiplied by 3, 768. So you will have 768 dimensions at the input for your tokens. And like that, you will have 4096 tokens because you have totally 4096 patches. Okay. Now what is done is 768 is not the dimensionality of your embedding space in this vision transformer model. It is actually 1280. So somehow this 4096, 768, this 768, you have to convert it into D dimensions, where D is equal to 1280 so that it fits the vision transformer embedding dimensionality. For that, you use a linear projection. So this is where patches are converted into embeddings. Of course, here position embedding also will be added, which will be learnable parameter. But I'm skipping that because we have discussed those details earlier when we discussed about vision transformer. So 4096, 768 will be converted into 4096, 1280. So this is the number of tokens. This is the dimensionality of the embedding space. Now these tokens will have token sequence, position embedding, resulting in input tokens. They will pass through transformer encoder blocks and they will be converted to context vectors. So how many context vectors do we have? Do we have 4096 or 1280? Which one is the number of context vectors? 4096, because 1280, please note, it's the dimensionality of the embedding space. 4096 is the number of tokens. Why? Because each the resolution was 1024 by 1024. Each patch was 16 by 16. So 1024 divided by 16 is 64. 64 multiplied by 64 is 4096. That is the total number of tokens. That is the total number of context vectors. Now, one thing you have to do is, this is now a sequence in a flattened form. But for creating masks, you don't want the flattened form of sequences. You still need the spatial information preserved. So first what you do is you reshape this 4096, 1280 into this kind of a shape. So basically you split 4096 back into 64 by 64. So you will have spatial resolution of 64 by 64 and your dimensionality will be 1280. So this 1280 is now the embedding space dimensionality in the vision transformer. 64 by 64 is basically number of patches along the width, number of patches along the height. But are these the original patches? No, these are the transformed patches because the patches have been passed through the transformer, the vision transformer. And finally, after this reshaping, what is done is this 1280 was fine for the embedding space of the vision transformer. But that embedding dimensionality is not good for the, or it does not fit the decoder later. So you have to transform this 1280 dimension into 256 dimensions. Okay, please explain and reshape. So reshape is simply this. See, there is no need of diagram. 1280 is simply, it is equal to 64, sorry, 4096 is simply 64 by 64. So in Python, basically you use the reshape command so that you can split 4094 as a linear sequence into two-dimensional sequence of 64 along the height and 64. Basically, it's the opposite function of flattening operation. This 1280 will be the first dimension, which is the input, which will be the embedding dimension. Now, embedding dimension for vision transformer and embedding dimension for the image, the mask decoder, which is about to come, are different. So the mask decoder's embedding dimension is 256. So you have to prepare your data. So now this is you can't call this as context vectors. You could have called them as context vectors over here, but here now they are having a different shape. So you can call them as maybe features, context-rich features. Okay, context-rich features. And these features now have 64 by 64 as the two-dimensional spatial information dimension, but the total number of dimension of each such patch is 1280, which is the embedding dimension of vision transformer. But then you change it using a linear projection from 1280 to 256. So your final output, which results from image encoder, will be 256, will be of the dimension 256, 64, 64. 64, 64 resulted from your patches. You had 1024 dimensional image, which was divided into 16 patch size. So this was 64 multiplied by 1024 by 16, which is also 64. So that is how 64 and 64 resulted. But you only had 3 RGB channels, but that dimensionality in vision transformer, it had become 1280. Then that 1280 is projected back into 256. So now your embedding dimension at this point will be 256. And the spatial information, the spatial dimension will be 64 by 64. Correct. 256 after projection is token embedding. Correct. So tokens will be in an embedding space of 1280, but after projection, they will become of dimension 256. So each token will be 256. Like that, if you were to flatten these tokens, you will have 4096 tokens. of each 256 dimensionality, but you are not flattening it. You are keeping it spatial with the spatial information preserved. You are keeping it like a 2D grid, basically. So image encoder part is actually simple because you know about vision transformer. So this part is basically simple. You are converting this input, which was 3, 1024, 1024 into. So ultimately what happens is input was 3, 1024, 1024, where 3 was the number of channels, 1024 was the spatial dimension. That got transformed into 256, where 256 you can imagine to be number of channels, which is also same as embedding dimension, 64, 64. And you know that this is also what happens in any CNN layers. In CNN, your spatial resolution, spatial dimensionality shrinks, your channel dimensionality expands. Exactly that is what has happened here. Your channel dimensions expanded from 3 to 256. Spatial dimensionality shrunk from 1024 to 64. Why projected back to 256 instead of 768? If you are asking about this 256, it's because 256 is the dimensionality that is expected by the decoder later. So that you will see in the next step. So, okay, so this is what has happened in the image encoder. Now, I did not explain to you this sentence like masked auto encoder pre-trained VIT. What does this mean? So this was a very fascinating concept. So auto encoder is actually a very simple architecture. So I'll explain briefly. I won't spend too much time here, but I'll explain briefly what is this masked auto encoder. So masked auto encoder was this. You will have an image which will be divided into, let's say, 100 patches. Out of this 75 patches, you will mask. You will have only 25 patches remaining. You will take those 25 patches, you will pass that through an encoder. Encoder will create an encoder representation of those 25 patches. 25 patches that are visible, 75 are hidden. Now, then, along with these 25 patches, you will also add some learnable tokens corresponding to those missing 75 patches to reconstruct a sequence of all the tokens. So here you have tokenized versions of every patches where red color is the visible patch, red color is the embedded version of the visible patch, black color one is the embedded version or the learned mask tokens corresponding to the hidden patch. And now using this embedding, which you will pass through a decoder, you will try to predict the image back where what you're trying to predict is if these are the masked patches, you are trying to predict what the pixels of those mask patches should be. So essentially you hide bunch of patches in an image. Now from the remaining patches which are not hidden, you will pass those visible patches through an encoder. Encoder will convert them into embedding representations. These embeddings are now expanded by adding the learnable mask tokens also. And now this combined embedding will be passed through a decoder to finally produce the output image. Now this output image, if the produced versions of these hidden patches are completely different from the ground truth, the loss will be very high. And because of this, the encoder and decoder will try to make better and better embeddings. But as this whole thing is called auto encoder, as this auto encoder becomes better and better, it will become better and better at predicting what the values of these hidden patches are. So essentially, this auto encoder is really good at teaching about image because you are randomly hiding certain parts of the image. And if the model is able to predict, even while the parts being hidden, if the model is able to predict what those hidden parts are, it's a good model. It understands the image. If you remember in BERT model also, exactly analogous thing was done. There some tokens were hidden using mask tokens, and the values of those mask tokens were predicted using the BERT model. Here in this autoencoder, what is predicted is the patches themselves. Now, if this encoder was a vision transformer model, then that resulting trained vision transformer is called as masked autoencoder pre-trained vision transformer, because now this vision transformer would have learned. Please remember, vision transformer originally was used for classification. You will have a class token, and then if you train the vision transformer such that the representation in that class token is really, really good, then vision transformer is really good. But here it's not classification. Here you will use all the tokens that are resulting from the vision transformer. So these are the patches that are fed into the vision transformer. It will convert them into embeddings. And if these embeddings are good, and then if these learned mask tokens are also good, and if decoder is performing really well, you will produce a very good image, which looks exactly like what the original image was supposed to look like. And when you train this for many, many times, your vision transformer will really become good at what? Will it become really good at classification? Maybe if we try it for classification, maybe it will be good, but it will be really, really good at understanding images. Why? Because this vision transformer encoder was used inside a mask and masked autoencoder, where classification was not the primary task, where understanding the image was the primary task. And this vision transformer, this pre-trained vision transformer, is what was used in the image encoder used in the segment anything model. All right. So that brings us to the end of part one. So part one is just the image encoder. Now let's move on to part two. So part two is the prompt encoder. And if you go through the paper, in my opinion, this will be the most confusing part, simply because I feel like they could have done they have drawn the figure in the perfect way. Maybe they could have drawn one more version of the figure to make it easy for maybe beginners. But anyways, now please understand, although they have written it like this, this figure might make it look like this part, which is supposed to be the prompt encoder, has only points, boxes, and text going into the prompt encoder. Mask is going into something else. But instead of saying like this, a better way to say is this whole thing is part of prompt encoder, in which mask is treated in a different way. Points, boxes, and text, they are treated in a different way. So you can think of prompt encoder as something with two different branches, where mask tokens, which are, as I said, dense tokens, dense prompts. Dense prompts are dealt in a different way. Sparse prompts like points and boxes are dealt in a different way. Text we will not be discussing, because as I mentioned, text was for using text, you will need a clip-based model. Now, there was a question, if we were using clip-based model to convert text into embedding, why do we need a prompt encoder? Because in the encoder, the dimensionality that results from the clip-based model and the dimensionality that this mask decoder is expecting would be different. So prompt encoder is needed in that case also. So mask, which is a dense prompt, is treated differently than sparse prompts, which are points and boxes. Now, another interesting thing which you may not notice is, in prompt encoder, there is no transformer. This is very surprising, right? You might think when you hear the word encoder, you might expect transformer, but there is no transformer here. So what do we mean by encoder here then? We will see. So just understand this. Image encoder is vision transformer. So obviously there is a transformer here. Prompt encoder has no transformer in it. Mask decoder, of course, will have transformer in it. Okay. Now, here is a different version of the diagram that I have created, which will look complex in the beginning, but I'll try to make it as simple as possible. So let's focus on just the red color boxes for a moment. Okay. So this entire yellow color box with black outline, this is the prompt. This full thing is the prompt encoder. This is the part of the prompt encoder. Red color is the part of the prompt encoder which deals with sparse prompts. This green color part of the prompt encoder is the part that deals with dense prompts. Okay. So now this point prompts, which are sparse, it will pass through this part. It will come out here. Box prompts, which are again sparse, which will pass through here, come out here. So please note, point prompts and bounding box prompts are not taken, it's not processed through this part. Mask prompt, which is a dense prompt, is processed through this part. Now, let's see what this looks like. Point prompt is, let's say I have n points, which I'm clicking. I will have n points. Each of them will have xy labels, xy coordinates, and then they will have labels corresponding to whether it's a background point or foreground point. So label will be foreground or background, which can be represented by 0 or 1. So this is n comma x comma y comma label. N is the number of points. For each point, I will have x comma y comma label. Then bounding box prompt is, again, if I have, let's say, m bounding boxes that I'm providing as part of the prompt, each bounding box will have one corner. So x1, y1 is the corner number 1. x2, y2 is the corner number 2. Okay. Now, what should I convert this into? If I'm converting these prompts through the encoder into certain dimensionality, what should that dimensionality be according to you, based on what you heard so far? Of course, it should be decoded dimension, but what should that be? Should it be 4096? Should it be 1280? Should it be 1024 or something else? It has to be 256, correct? Why? Because here we already discussed in vision transformer, in the image encoder part, we already discussed that the final thing that comes out of here is of 256 dimensions. And that is the dimensionality that the decoder is expecting. So here in prompt encoder also, we are trying to encode, if we have n points, we are trying to encode these n points into 256 dimensional space. So here coordinates will be normalized, mean and standard deviation. There will be a position embedding added. So this position embedding is an is a learnable position embedding vector. It will be added. And then this you can simply convert. So these x comma y comma label, it's a triplet. You can convert that into a 256 dimensional vector just by projecting. So what does this encoder do now? It simply converts every point. So let's say n was 1. Each point is represented using x comma y comma label, let's say background or foreground, let's say 0. So x is, let's say 1.2, y is 2.6, and if it is background, let's say 0, this will be converted into a 256 dimensional vector where each dimension will have some value by performing projection. Similarly, bounding box prompt will also be converted into an output of dimensionality 256. Why label is only required for point prompt and not box prompt? I think that is because in point prompt, when you are clicking, the user might be, I mean, this is for training. It might be a bit ambiguous whether the user clicked exactly that particular object in the foreground or the object just behind that. In box, the size of the box is anyway big. So there are large number of things that are enclosed inside the box. So it doesn't make sense to say, I am now looking at everything's inside this box, but in the background. But because usually we draw boxes around the foreground objects only. Maybe that is why there was no requirement for foreground background distinction for box, but point can be a bit ambiguous. Now, is position embedding encoded to 256 dimension? Exactly. Position embedding will be also be a 256 dimensional vector. And what is the purpose of position embedding in point prompt? Because the point comes with a position information, a 2D position information. So we want to somehow make the model. So the XY 2D information is already there by clicking the prompt. I mean, clicking the point. It's already there in the input. But what they wanted to do was they wanted to have a learnable position information added extra. I think a better term to call this is position embedding bias or something. It's a better term because it's being added. So they wanted to incorporate a learnable position vector also to the original position embedding, so that maybe that can learn a few more things. Usually position embedding is added so that the people who are creating it will hope that in the back propagation process, this position embedding vector will automatically transform to something that is useful, right? In bounding box, can you note that the embedding vector is 256 dimension, but there are 2m points. Why 2m? What is this 2? Because there are two corners corresponding to every single bounding box. So if you have one box, you will have two vectors resulting from it. Each vector will be of dimension 256. In this case, m was the number of boxes, and here n was the number of points. Okay. So finally, your n point prompts are converted into n vectors of 256 dimension. Your m bounding boxes are converted into 2m vectors of 256 dimension. Why 2m? Because every bounding box is defined by two corner points. Now, so this is what happens to the point prompts and bounding box prompt. And now what about mask prompt? Mask will be a binary mask of original dimension that of the original image. Image was 3, 1024, 1024. For mask, there is no RGB concept. Mask is just binary. So it will be just one channel, but same spatial dimension as that of the input image. Now, obviously, this also we cannot keep as one channel. It has to be converted to 256 channels. So mask is first converted to 256 channels, but spatial information of the mask, instead of retaining it as it at 1024, 1024, using 2D convolution con 2D operation, you can convert it into 64, 64. Now, what does this resemble? This dimensionality resemble? It resembles the output that was coming from the vision transformer. That was also 256 channels. 64, 64 was the spatial dimension, right? So now mask is converted into higher number of channels, lower spatial dimension, just like what you did with the image. But to convert image from that high spatial, low channel dimension to high channel, low spatial dimension, you use vision transformer. Here, there is no vision transformer. It's simply 2D convolution operation. And here also, I don't think there is a learnable position embedding in this case. I have to check that. I'm not 100% sure. I don't think there is a position embedding added in this case, because anyway, the whole mask is not one point. It's just the whole thing. So this is prompt encoder in a nutshell. Now, for you to understand this image fully, because you see a plus sign here, you see something going here, something going here. So to understand this fully, we have to also go through decoder a little bit. Okay, so we will come back to this image after going through the whole architecture. Are 1024 number of points? Yes, 1024 by 1024 are the pixels, XY pixels in the mask, just like how 1024 by 1024 was the original dimension of your image. Your input image was 3, 1024, 1024, which means if I am inputting a mask, the mask has to be based on this image, right? So same, but mask is binary, which is why there are no 3 channels. It has only 1 channel. All right. So now, okay, this I already discussed. One branch of the prompt encoder is responsible for sparse prompt. The other one is responsible for dense prompt. This I already discussed. This also I already discussed, but I want to just walk you through this. So point prompt has XY coordinates plus foreground background label. It is processed through sparse branch of the prompt encoder, just like bounding box also. And the token finally will be converted to 256 dimensional. Bounding box will have 2 points per box, which means the output will be 2, 256 per box. If there are m boxes, it will be 2m, 256. Here it will be n, 256 if it is like n points. Mask, we will start as 1, 1024, 1024, which will be where channel dimension will be expanded to 256. Spatial dimension will be shrunk to 64, 64. Text is not directly supported in SAM. It has to be passed through a clip encoder. We will not be discussing that today. Now, the token sequence in encoder for points, as I mentioned, there is position embedding plus type embedding. So type embedding is another learnable embedding, which says whether it's a point type, whether it's a corner 1 type or corner 2 types. So there are 3 types of things, right? A point which you click in an image is a point type. Then a box that you are drawing in an image, it has C1 and C2. So to annotate that this is corner 1 and corner 2. Now, corresponding to the fact that this is a point, you can define a 256 dimensional learnable type vector. Type vector meaning that vector will try to learn that this is a point. Similarly, corresponding to C1, there will be a learnable type vector, which will again be a vector which will try to learn the fact that this is corner number 1. Then second vector, which will correspond to corner number 2, will again be another learnable vector of 256 dimension, which will try to learn the fact that this is corner number 2. So there is position embedding vector, position encoding vector plus type embedding, both of which are 256 dimensional. Now, this is the case with both bounding rectangle and the bounding, the individual points. Now, one thing that is done is you concatenate this along token dimension, but if I just draw it, if I just say this, you will not understand. But let me show it from maybe I'll show this to you in a moment. Like you have two outputs here, right? N comma 256, where n corresponds to number of points. 2m comma 256, where m corresponds to number of boxes. How many learnable parameters? Maximum number of points in boxes. I think the learnable parameter will correspond to, no, there is no multiple learnable parameter corresponding to multiple points. The learnable parameter tries to encode the fact that one is a point, one is a corner number one, and one is a corner number two. So number of learnable parameters will be for points, irrespective of number of points, it will be one. The learnable, not learnable parameters, learnable embeddings, the number of learnable embeddings corresponding to bounding box will be two, irrespective of the number of bounding boxes. It just needs to learn it is corner one, the other is corner two. But it doesn't depend on the total number of corners or total number of points. Then it will be ambiguous. Then it will not be clear while training how many number of learnable vectors you have to define. Okay, this also I discussed. Dense prompt is converted first from 1024, to 64, then this is expanded to 256 dimension. So ultimately, channel dimension is expanding, spatial dimension is shrinking. Now, what comes out of the prompt encoder is the collection of sparse prompt embeddings, the collection of dense mask embeddings. Now, sparse prompt embedding will include points and corners corresponding to bounding box. Dense mask embedding will only involve mask. Is channel dimension the token embedding? Correct. Channel dimension is the token embedding, which will be 256. Now, before we pass all of this into mask decoder, we have to also understand that there is one more thing. So as we discussed, mask decoder somehow produces the final mask, right? Somehow this produces the mask output. But what all things should go here? Into this mask decoder, somehow I should pass 256, 64, 64 dimensional output, which comes from the image encoder. I should somehow pass the n, 256, which is coming from the point encoder. I should somehow pass 2m, 256, which is coming from the box encoder, which is the same. I'm just writing point and box just so that this is distinguished. If there is a mask, I should also pass 256, 64, 64 corresponding to mask. Should I call this as mask encoder? Yeah, maybe mask, mask prompt encoder. Is that it, or am I missing something? Yes, there should be some sort of mask query, some initial mask. So what is done is that also we have to pass somehow here. So, and how many masks did we discuss we are producing as the output? Total number of masks per forward pass, it will be 3. So actually, there are not just 3 tokens, or rather, there are not 3 inputs, 4 inputs are passed here. 1, 2, 3, these are corresponding to masks. And the last one will be converted into IOU scores. IOU score when you compare the predicted mask with the actual mask. And you don't need 3 separate vectors for IOU, because within one vector, you can output a sequence of 3 numbers. We'll come to that. Okay. So total number. So now look at the output that is coming out from the prompt encoder. One is n, 256. Another is 2m, 256. This is 4, 256. Why? Because you have 3 corresponding to 3 masks, 1 corresponding to IOU, and 4, 256. Mask is anyway dealt separately. Okay. But these 3 guys, this point prompt encoder, box prompt encoder, and you can call this as mask query encoder, but I don't think that is the right term that they are using in the paper. So 4, 256, because see, here actually we are outputting 3 masks and 3 IOU scores. These 3 IOU scores are output as just one single list. So basically, I need 3 masks and 1 list which outputs the IOU scores. So if I want 3 outputs, I have to start with some, I mean, if I want 3 plus 1, 4 outputs, I have to start with 4 queries, just like the queries that were there in the detection transformer. In detection transformer, we were predicting 100 output masks, which means it started with 100 object queries. Just like that, here I need to predict 3 masks, one mask corresponding to the bigger level object, one mask corresponding to a bit more, because the user inputs are ambiguous, as I showed you, the emu's entire body versus just the upper body versus just the face. So there were 3 masks that were getting output, plus corresponding IOU scores as a list. So 3 plus 1, 4 outputs is what I am expecting from the decoder ultimately, which means I need to start with something. I need to start with 4 separate values, which will get transformed into these 3 masks and IOU scores. So this 4, 256 is 256 dimensional initial embedding corresponding to mask 1, 256 dimensional initial embedding corresponding to mask 2, 256 dimensional initial embedding corresponding to mask 3, and 256 dimensional IOU scores corresponding to all the masks. So the total number of these items are 4. So it will be 4, 256. So there are 4 items, each of dimensionality 256. Now, point encoder, there were n points, there were of 56 dimension. Box encoder, box prompt encoder, the output was 2m points because there were 2 corners per box. There were m boxes, each of them were 256 dimension. And this input is of total number. There are 4 items, each of them are of 256 dimension. And unlike detection transformer, here what is done is concatenation is done. So this, and this are concatenated to become n plus 2m plus 4, 256. So you will have a sequence going into the mask decoder whose length is n plus 2m plus 4, where n is the number of points, m is the number of boxes, 4 corresponds to 3 masks and 1 vector, which will be corresponding, which will finally be converted to IOU scores. So you will have a sequence of 256 dimensional vectors, and the sequence length will be n plus 2m plus 4, which will be passed into the decoder along with something else. So now, where is this n and 2m coming from? Is that coming from the image encoder or prompt encoder? This n and 2m? It is coming from prompt encoder. Where is this 4 coming from? Is that coming from image encoder or prompt encoder? This 4, the number 4, is it coming from image encoder or prompt encoder? Neither, right? It's not coming from image encoder or prompt encoder. They are initialized so that decoder can finally produce 4 output. So these are simply initialized, randomly initialized vectors of dimension 4. These 3 sets of vectors are concatenated. Each of their individual dimension will be 256. Concatenated meaning they will be converted into one sequence of vectors. Each vector will be of dimension 256. And now this whole sequence can be passed into mask decoder. But then there is the question. We are still missing the input that is supposed to come from the image encoder. Image encoder was finally outputting 256, 64, 64. We did not discuss about that yet. One thing we have omitted so far is, what about this mask prompt, which was of 256, 64, 64. Where is that? So what is done is this 256, 64 plus 64, which results from mask encoder, is directly element wise added to this mask prompt encoder, which is also 256, 64, 64. So when you element wise add these two, what will be the resulting dimension? It will be the same. Element wise addition will not change the dimensionality. It will be 256, 64, 64. Now that is what will be the other input into the mask decoder. Okay. So now Now, if you go back to the original image, it will make much more sense. Now let's look at this. This original image is from the paper itself. Let's start from the beginning. You have input image. Input image is passed through vision transformer, which was pre-trained on masked autoencoder, and it produces image embedding, which will look like 256, 64, 64. Points initially will look like n, x, y, which will be converted to n, 256. Box will look like 2m, 256. My drawing is a little bit bad. 256. Text is not there. Mask. Do you understand why this is shown? Why it is drawn like this? This is to show downscaling or downsampling. If it was drawn like this, it is like upsampling. So this is to show that from 1024 dimensions, spatially, you are shrinking it to 64 dimensions. So here it will be 256, 64, 64. Now this mask output from the mask prompt encoder is added. That's why you see this plus button element wise added to this guy, which is the output from the image encoder. And that is now one input that goes into the mask decoder. One thing that is not shown here is the initialized 4 vectors corresponding to the mask and the IOU. But this n, then the 2m and the 4 corresponding to 3 masks and 1 IOU will be converted into one single sequence, and that will be passed into the mask decoder. So now hopefully this diagram makes more sense to you. Hopefully you understand what is the relevance of this plus symbol. This plus is because this is element wise added because they are of same dimension. So image information, image encoded information, and mask encoded information are added together element wise, and that is passed into this. So now this is purely image info. Points, boxes, plus the initialized mask and IOU, they are passed into the prompt encoder. Now, in neither of these, there is a transformer. This is purely projection operations. There is position embedding added, but there is no transformer in either of this. Okay. Now, mask decoder, we can go into the details of mask decoder. It will be very interesting now. So just look at this. Everything entering the mask decoder. Image embedding will be 256, 64, 64. This let us ignore for a moment. Let's just consider that it is 256, 64, 64. Dense mask prompt is also 256, 64, 64, which is output from the mask prompt encoder. Sparse prompts are n, 256. Here actually, this n simply means the total number of points plus total number of corners. Both are counted in this n, okay? So when I said n plus 2m, this capital N is basically both n and 2m. Then output tokens are tokens which will finally result in my three masks and one IOU score list. So that is this 4. So this n plus 4, which according to our previous discussion was n plus 2m plus 4 of 256 dimension, will enter the decoder. Then this 256, 64 plus 64 added with this, these two will be added together, will enter into the decoder. Initialized mask is not 256. It is initialized mask is not 256, 64, 64. Why is it 4, 256? Yeah. So to produce the final mask, we are not directly utilizing the mask token. You will see that in a moment when we come to the mask decoder. Like your question is, if the final mask that we are producing is something like 1024, 1024, because ultimately the mask has to match the spatial dimensionality of the image. So final mask is 1024, 1024. So yeah, your question is then, why are these masks initialized as 1024, 1024, right? Because that will be so huge in spatial dimension. We are anyway not representing anything in the token embedding space as 1024, 1024. The embedding dimensionality, irrespective of what token it is, whether it is a mask output token, whether it is a prompt sparse embedding token or mask dense embedding token, Everything is embedded as 256 dimensions. Now your other question could be, okay, it is 256 dimension, but then why are we keeping spatial dimensionality? Why are we not keeping spatial dimensionality as 64, 64? That will be answered when you look at the architecture of the prompt decoder, because prompt decoder takes care of converting the tokens into 64, 64. I'll show you that. Okay, so this we have already discussed. Now let's look at what happens to these guys. So I showed you the image till here. Till here, I did not show what happens after that. So these two are concatenated, n and 2m, which I already showed you, n plus 2m comma 256. Then there are 4 output tokens, 3 corresponding to mask and 1 corresponding to IOU. So n, and then these two are concatenated. So the output will be n plus 2m comma n plus 2m plus 4 comma 256. So this is one input that goes into decoder. The other input will be two things added. So what is added here is image encoder output of dimension 256, 64, 64. That will be added here along with the mask. And then this is the other input that goes into input 1 that goes into decoder, and input 2 that goes into the decoder. Now we have to see further how decoder takes care of these things. Okay. So now let's look at the mask decoder. This diagram is actually pretty much same as the diagram that is there in the paper. I have just drawn it in the reverse. I mean, right, instead of right to left, I have drawn it from left to right, or vice versa. So this is the diagram from the paper. Let me show you. So this is the diagram from the paper. So what I have drawn is almost exactly the same thing. It's just that for me, it was convenient to draw from right to left, but it will be the same. In this decoder, of course, there will be transformer, because to perform conversion of these context vectors into my final output, I need some kind of transformer architecture. And of course, I should also have cross attention here for sure, because I have two streams of inputs coming. One stream of input is the input coming from the image plus mask addition. The other stream of input is coming from the 4 plus m 2m plus n. So that is the other stream of input. So first, let me show you the entire image, and then I can come back to decoder separately. Maybe this is more sensible now. Now, whatever is coming out of my 4 tokens plus point plus box, that is passed into the self-attention. So this, I hope you can see this blue line. So into the set, so order is this. So it goes from top to bottom. This is the arrow flow of the arrows. Just be aware. Okay. So this output is passed into the self-attention, and these tokens, n plus 2m plus 4, those tokens will pay attention to each other to create that many context vectors. So how many context vectors will be there here? At this output, the total number of context vectors will be equal to what? It will not be 256. 256 is the dimensionality of the context vector. It will be n plus 2m plus 4. That many context vectors will be here. Queries will be created from which tokens? From this token. Keys and values will also be created from the same set of tokens, which means it is self-attention, because I'm using the same sequence to create queries. I'm using the same sequence to project it into key and value space. So it's a self-attention because you are paying attention from one sequence to itself. Then here into this, you are passing whatever output is coming from your mask plus image element-wise addition. So now this green, I can call this as maybe image sequence. This I can call as point or text sequence, I think or token sequence. Okay, so token sequence is coming in this blue color line. Image sequence is coming in this green color line. And here, a cross attention is created between token to image. What does that mean? What do you think is getting converted into the query? Is this stream getting converted into the query, or this is getting converted into the query? When I'm saying token to image cross attention, Is query resulting from token or is query resulting from image sequence? The query is resulting from token sequence. So token sequence is these sequence of n plus 2 n plus 4 tokens. They are projected into the query space. And that query will pay attention to keys. So query.key transpose, where keys will be resulting from this sequence. Okay. Now here you might wonder, this is not a sequence. This is 256, 64, 64. So I have to convert this into a sequence. How does this look like when it is converted to a sequence? Can you tell me what is the sequence length? Because image input, if you remember, it was 256, 64, 64. And what is the sequence length here? It will be 4096. That many tokens will be there, each of dimensionality 256. Here, n plus 2, m plus 4, that many tokens will be there, each of dimensionality 256. Now, query is basically the context vectors corresponding to the token sequence projected into the query space. Key and value are the projections of this image sequence, this flattened image sequence projected into the key and value space. Okay, so that is why it's called token to image cross attention. And why the word cross attention? Because query, the origin of the query, origin of key and value are different. Now, here is my question. How many tokens will be coming out of here? Is it 4096 or is it n plus 2, m plus 4? How many tokens will come out over here before passing into multi-layer perceptron? The number of tokens. So there are, I can see few responses. N plus 2, n plus 4. It's not queries multiplied by keys. Please note, queries multiplied by keys is basically the context vector, the attention weight matrix. Okay. The number of queries multiplied by key is just the matrix. The number of the total number of tokens that are coming out of here are basically context vectors that are going in here. So whatever vectors that are going in as input here are converted into context vectors here. So n plus 2m plus 4, that many tokens were passed here and they were converted into query. So the final context vectors that result from an attention operation will be same as the total number of queries. So the total number of queries is not 4096. 4096 is the total number of keys and values. N plus 2m plus 4 is the total number of queries. So the output sequence length that will be passed into the multi-layer perceptron will be n plus 2m plus 4. Now, after multi-layer perceptron, something happens. So let's ignore this branch for a moment. Let's look at this image to token sequence. In image to token, these n plus 2m plus 4 are, again, these many context vectors of 256 dimension. It's passed here. And similarly, here you have 256 dimensional tokens of sequence length 4096. Now here, who is creating the queries? Are the queries created from the input tokens? I mean, from the token sequence, or are they created from the image sequence? They are created from the image sequence. Queries are created from the image sequence. Keys and values are created from the token sequence. And because the queries and keys are coming from different sequences, it's a cross attention, it's not self attention. Now tell me, what is the total number of tokens that will come out of this? Over here, how many will be there? 4096 will be there, but one more operation will be performed to reshape the 4096 back into 64, 64. Because ultimately for mask, I don't need a flattened 1D sequence. I need a 2D sequence. So just for the purpose of performing self-attention or cross-attention, this 256, 64, 64 will be reshaped to 256, 4096. But once this calculation is done, it will be reshaped back from 4096 to 64, 64. And the dimensionality of each of these will be 256. So it will be 256, 64, 64. Now there is a 2x mentioned here, 2x, which you will see in the paper also. It simply means this whole block is repeated twice in series. So you can see that 2x here. So this whole block repeats twice in series. Okay, so now let's take a step back. Let me recap what all things are happening, because a lot of things we have discussed so far. Now is the last part. So let's start with the input image. Input image was 3 by 1024 by 1024 converted to patches. So you had total 4096 patches. Each had 16 by 16 by 3, which was 768 dimensionality, which was projected to 1280 dimensions, so that this fit the vision transformer embedding space. Vision transformer converted this into 4096 context vectors, each of dimensionality 1280. Then this 4096 sequence was reshaped to 64 by 64, and this 1280 was projected to 256 dimensional space, so that we had the final embedding dimension that of the decoder. Then in prompt encoder, we had point prompts. The n point prompts were converted to n vectors of 256 dimension. The m box prompts were converted to 2m vectors of 256 dimension. Mask prompts, which started with 1024, was converted spatially into 64 by 64, but the channel size was 256. Now this mask is element wise added to this output coming from the image encoder. So this and this are added, 1 plus 2. This is added to produce this output. So this is the first, let's say, output 1, or rather I can call this as input 1, which goes into my decoder. This is the other input which goes into the decoder. Input 2 is the other input that goes into the decoder. What is that? That is the addition of the n points, 2m corresponding to box, and 4 corresponding to my output token. So total n plus 2m plus 4, that many tokens go into the decoder. Both of these token sequences are of 256. However, here 64, 64 has to be temporarily reshaped into 4096, so that transformer can take it as a sequence. Now self-attention is between this sequence of n plus 2m plus 4 tokens. So here the resulting context vectors sequence will be of length n plus 2m plus 4, but their embedding dimensionality will be 256. Here token to image cross attention is created, where tokens are queries resulting from these input tokens. These images are basically the keys and values resulting from this sequence. So that is token to image cross attention. So this you can also call as bidirectional cross attention, because in this whole block there is token to image cross attention and image to token cross attention. Both are done. Okay. So here the output that was coming out was equal to total number of queries. Total number of queries was n plus 2 m plus 4. Here, on the other hand, the output that comes out is also same as number of queries, but here the number of queries was not n plus 2 m plus 4. That was 64 by 64. So total number of tokens coming out here is 4096, each of dimension 256, but then they will be reshaped to become 256, 64, 64. Okay, so far so good. Now we are almost at the end. Now we need to do two more things. We need to finally create masks, 3 masks, and the IOU scores. Okay. So now let's see first what happens to this sequence. This 256, 256, 64 is passed here. So 256, 64, 64 is passed here. Okay. And here an image upscaling is applied such that the spatial dimension is upscaled twice, 2 times. So what happens is, after this image upscaling, which is simply a convolution upscaling operation, it will look like 256, 256, 256, 256. Because 64 times 2 is 128. 128 times 2 is 256. So image upscaling to double the size will happen twice. So in the original paper figure also, you can see the same thing. 2x convolution transformation. So convolution transformation that upscales the spatial dimension. So the final output which comes out of this will look like this, where this is the spatial dimension and this is the channel dimension. Here spatial dimension was 64. Here it became 4x because 2x is applied twice. Now here the same 256, 64, 64 is passed here. And here, what is being passed over here? Just from the diagram, what do you think is coming here? N plus 2m plus 4 comma 256, that is coming here, right? So now this blue color is the token sequence. This is the image sequence. And here again, one more set of attention is done where token to image cross attention is done. Now here is a question. Okay. Finally, do we care about the context vectors corresponding to this entire sequence of n plus 2, n plus 4 tokens? Do we care about, in vision transformer, for example, did we care about the context vectors corresponding to every single tokens in the sequence? No, we only cared about CLS token. Similar to that, here, do we care about this entire n plus 2, n plus 4 context vectors corresponding to all those tokens? We don't care about that. We only care about the 4 tokens. So we can extract just those 4 tokens which were initially concatenated at a particular position. So that position alone we can take out here after this cross attention is applied. So that position, so corresponding to IOU, there was a position. So the context vector corresponding to that particular position can be extracted. Okay. Similarly, for the mask tokens, we had 3 mask tokens. Okay, there is one more question. Why is cross attention applied twice? I also asked the same question myself. So my understanding is, this we know why is this being applied, because finally the context vectors that we need are corresponding to the token queries. We don't need the context vectors corresponding to this 4096 queries. Why? Because the context vectors that are of interest for us are those 4 context vectors, and those 4 context vectors can be found in the sequence of n plus 2, n plus 4. It's not found in the sequence of 4096 tokens. So for that reason, if any cross attention was being applied here, it has to be token to image cross attention, not image to token cross attention. Do you understand that logic? See here, if at all we were applying any cross attention, it has to be token to image cross attention, not image to token. Why? Because if we did image to token cross attention, the resulting context vectors would be coming from my image sequence, which are those corresponding to the sequence of 4096 tokens. But I don't care about that. For my final output, I care about the 4 tokens present in the sequence of n plus 2, n plus 4. So for that reason, it makes sense why we are doing token to image cross attention. Now, you could ask me why they did not do image to, instead of doing token to image cross attention here, do image to token here, then do token to image here instead of image to token. Then maybe I could avoid this cross attention. But then for image upscaling, again, I need my, this token to image cross attention is not useful for my image upscaling. Why? Because here I'm getting the context vectors corresponding to my tokens. I need context vectors corresponding to my image for performing image upscaling. So if we were to eliminate this cross attention, I think we might have ended up with another cross attention over here, which does image to token cross attention. So simply because I need both sequences. I need image sequence as well as token sequence. There is y cross. We can get that from. Can you explain where we can get that from? Above meaning from where? From here? If we take it from here, it's useless because then the double cross attention, bidirectional cross attention has not been applied yet. Let me first erase all of this. So my logic is, so here, this is very context rich. There is no doubt about it. Whatever comes out of here, the image sequence is very, very context rich because it came out of the result of bidirectional cross attention. If we take something from here, it is not context rich. It has not passed through multilayer perceptron. It has not passed through bidirectional cross attention. Now, here, maybe what is being done is, already whatever is coming out of here has gone through one cross attention. Here, one more cross attention, maybe so that you can have symmetry, because here image sequence is anyway going through 2 cross attention. But since we are taking this from here only this sequence has only gone through 1 cross attention. So maybe to have that symmetry. But otherwise, if you are saying if you don't have this, if you directly pass this to MLP, this stream is not as context rich, because this stream has not gone through image to token cross attention ever. So perhaps that's the reason. I mean, if I were to try this for the first time, maybe I'll try without this cross attention. But maybe my thinking is the reason why the authors might have added a token to image cross attention was because of this. But it has to be token to image cross attention, not vice versa, because we need finally those 4 tokens. So what is done is, now you have 4 tokens. One token is passed through one MLP for predicting IOU scores. The other 3 tokens, the context vectors corresponding to other 3 tokens, are passed through 3 separate multi-layer perceptrons to produce 3 separate context vectors of dimensionality 256. So these will be vectors of one token of 256 as the dimensionality. And then what is done is, what is coming out of here is 256, 256 spatially, and channel dimension is 256. But I want my mask to be of something that looks like 1, 1024, 1024, right? Because only then I can superimpose this mask over my original image of 3, 1024, 1024. So how do you go from a 256 channel input into a 1 channel output? What you can do is, this token which comes out of MLP, which has 256 dimensions, you can simply do a dot product of that with these 256 dimensions. So that is why it says per mask dot product. So this token corresponding to, and you have 3 tokens like that, one corresponding to each mask. Those tokens are each of dimension 256. There is no spatial dimension. The dimensionality is 256. And that 256 dimensional token can be taken as a dot product with these 256 channel dimensions to produce a scalar, just basically a one-dimensional output at the channel dimension, and spatial dimension preserved as 256, 256. So that is what comes out of here. And then this can be simply expanded using interpolation to 1, 1024, 1024. This step is easy because it's like image resizing to a bigger size. You will interpolate the values. So that is what is done here. Let me just reiterate what happens in mask decoder once more by erasing everything. So in mask decoder, there are 2 streams that are the input. One is the token sequence and one is the image sequence. Token sequence undergoes self-attention to produce n plus 2, n plus 4, that many context vectors. Image sequence enters only here. Now token sequence is converted to queries, image sequence is converted to key and value, and cross attention is performed. And here n plus 2, n plus 4, that many context vectors will be there, which passes through MLP. Now that sequence again enters here, where that sequence is converted to key and value, where queries come from the image sequence. Now here, there are totally 4096 context vectors, which will be reshaped to 64 by 64. And those tokens are of 256 dimensions. Here, I will have n plus 2, m plus 4, that many tokens of 256 dimension. Now, these 2 streams are once again made to pass through cross attention, where token to image cross attention is performed. And the result is, from the resulting sequence, whichever position corresponds to my IOU token, that is passed through an MLP multi-layer perceptron dedicated for projecting IOU into appropriate dimensional space. And you will have 3 separate MLPs to take care of the 3 individual tokens corresponding to mask. The 3 tokens corresponding to mask will be converted to 256 dimensions. So there will be 3 streams, or each of 256 dimension. And this sequence, which is going in, was 256, 64, 64. But then image upscaling doubles the dimensionality of the space 2 times, because this is 2x image upscaling, which means spatial dimensionality will double first to 128 and then to 256. So this will become 256, 256, 256. And then to convert the channel dimension from 256 to 1, because mask has only one binary, it's a binary mask, so it has only one channel. This input stream of 256 dimensional mask tokens are performed a dot product with this 256 channel dimension, resulting in one scalar dimension, 1 comma 256 comma 256. So finally, what comes out of here is 1 comma 256 comma 256, which if you want to superimpose on top of an image of dimension 3 comma 1024 comma 1024, you can simply upscale this. You can upscale this to 3 comma 1 comma 1024 comma 1024. Yes, there are three masks. That is correct. So this is corresponding to just one mask token. Like that, there are three mask tokens. So totally like this, there will be three separate masks produced. So this is mask number 1, mask number 2, and mask number 3 also will be the same. That's correct. And corresponding to these three masks, there will be three IOU scores also. So this is the overall architecture of segment anything model. I won't say in a nutshell because clearly it was not in a nutshell, but this is how you understand about segment anything model in a very deep level. Now, coding segment anything model from scratch is almost impossible because this is a very big model trained over huge data set. But what we can do is we can perform some very nice inference. So now I'm going to open one Google Colab notebook, which I will share with you in a moment. So just use this link. Oh, use this link. I mean, there is nothing much to code here because we are simply taking a pre-trained segment anything model from a particular Facebook public checkpoint. And we are just passing an image, passing a particular XY point prompt. Okay. I just run the code and show you what the output looks like. So this is the input image, and this star is the point prompt. So this point prompt is basically the XY coordinate of the input point. Here, box prompt also can be input, but I'm just showing you point prompt. That is the simplest. And I'll show you how to change it. Here, mouse click is not possible on Google Colab, but I'll show you where mouse click is also possible. And this code is actually pretty fast to execute. You guys also try this, and yeah. So now see, because the point has come here. This is one of the masks. I'm not outputting all the masks here. It's masks of 0. Let me put masks of 1. Let's see how it looks like. See, this is mask of 1. So now mask of 1 is corresponding to just the upper body jacket. And mask of 2 will be, I don't know what that will be. Mask of 2, okay. Mask of 2 is upper body jacket. Mask of 1 was maybe the whole dress, perhaps, right? I can see some blue color here also. So that is mask of 2. Mask of 0 was the whole person, entire body of Rajat. So yeah, so mask of 0 is the 0th level mask is the entire person. Mask of level 1 is the just the jacket plus a little bit of the dress. Mask of 2 is just the jacket. So basically you're getting 3 level outputs. Then if you want to change the position of this point, you can just say this x comma y coordinate 400 instead of 600 comma 400. 800, put 600 comma 400, and inference is kind of fast. See, now it's on the dome, and if I put mask of 1, I'm not sure, not the dome, just the whole building. Mask of 1 means it's also looking the same. How about 600 comma 100 or 150? Okay, now, so this is mask of 0. Okay, I think this is a very good example, perhaps. See, mask of 0, 0th mask is the whole building. Okay, my selected point is over here. Mask of 0 is the whole building. Mask of 1 is just the dome. Mask of 3 is mask of 2 is, I don't know what that is. It's just the top part of the dome. It's amazing, right? Isn't it? I think if I move it to a bit more higher position, 100, this will be perfect. So see, mask of 2 is just the top part of the dome. segment anything model is trying to is able to understand that, it's ambiguous. When I click here, it doesn't know whether I mean to click the top part of the dome or the entire dome or the entire building. There is no mask of 4, I think, because only 3 masks are being input, right? Then if I give mask of 3, maybe there will be some error. Yeah, because only 3 masks are input. So 0, 1, 2 will be the maximum index. So here again, 0 means the entire building. That's the first level. 1 means the full dome, I think. Yeah, 1 means the full dome. 2 means just a part of the dome. It's really beautiful. Okay, just try this out with different, different inputs. I think it'll be very, very nice exercise. Now I want to show you one more website. So this Hugging Face Spaces, they have a segment anything model. This is the link. So you can go to Hugging Face Spaces and just search, segment anything model. Then whichever has inference, you can use that. So here I can upload an image, or I can just, yeah, let me upload an image. Okay, so this is the image. And then if I click here, hopefully, so first it extracts the image embedding, which will happen ideally only once. And yeah, see, when I click the sky, it's able to just get the sky. Then clear points. If I click the person's shirt, it's the full person. I'm not sure here, how do I get the other segments in this particular application? I'm not 100% sure if I can get, if I click just the, yeah, okay, now I can see. Oh, if I move my mouse pointer also, it's able to detect based on the hovering effect. Okay, pretty cool. So this also just try. And the even better thing is to just go to segment anything website. So just go to Facebook and not Facebook, segmentanything.com. And here you can just try it on their playground. This is the latest version of segment anything model, by the way, not the earlier version. But here you can upload any image. So the website, if you Google search segment anything website, you will come across this. And here it's text-based prompt. So they allow direct text-based prompt. So you can just type, let's say, buildings. And then it will search for buildings based on the text-based prompt, and all the buildings will be annotated. Then let's say add object or remove this and type hoop. Then it highlights the basketball hoop. And if I type shoes, see, now this inferencing part is very fast because image embedding is only created once. So this is pretty cool. Here there are, in this segment anything latest website, they have bunch of other things. I'll show you one interesting application here. You can even create 3D models from images. So here, for example, it segments the image first, and then I can select the person. So this person alone is segmented out, and there must be, yeah, and then it creates a 3D model based on that particular object. So this is, I think, SAM3 model. This is not the original model. I'm just showing you its capability. So it's like really amazing. And I'm sure this will involve extensive training on more data sets. And creating 3D scenes, I tried with some my own images. The output was not very good. But if I use their own images, it's very good. So let's say I take this and I click this couch. So then if I click this and generate 3D, this couch was coming out really good. But when I tried some giraffe or something yesterday, it was really bad. It looked so funny. I'll show you once. See, this is really cool. So it's segmenting, and segmented item is being converted from a 2D space into a 3D space. Um, Let me actually pick some animals or giraffe. So the giraffe which I created the other day was extremely funny. I just want to see if that can be reproduced. So let's upload. Okay, so first image will be converted to embedding, and then only we can select the object. Okay, so now embedding is done, object is selected, generate 3D. Okay, not so bad. Not the best of giraffes, but the one which I created yesterday was extremely ugly looking. This one is kind of okay. But cool model, right? I mean, this is the SAM3 model, um, not the original model that we were discussing right now. Um, so, but just try this out. Try out, read the not the documentation, read the landing page of this website to read about what they have advanced in SAM3. There is a question: why clip-based model for the text? We can we can use simple BERT-like text encoder anyhow. Yeah, we can use any encoder. The only thing is for training the SAM model, if you want to use Facebook's own pre-trained SAM, of course you have to use clip, because there they use clip-based embeddings while training. Clip the image embeddings created using clip was used for training. Because of that, text will have to be converted to embedding using clip. All right, so that's pretty much it, guys. I will this will not be coding from scratch, but I will recommend you to at least try out a few things in the Google Colab notebook. So just try out with box input. Text input here directly is not possible, but I can give you an assignment where you add a clip-based pre-trained model in addition. Use that to convert text into embeddings, and then pass that text, and then you should be able to type a prompt and just get the same thing. So prompt could be highlight the top part of the dome and get the same thing highlighted there also. Okay, so just try that out. I'm sure you're going to love it. So that will be the assignment for this week, basically adding an additional capacity of pre-trained clip. It's very easy. I mean, I don't mind you using any chat GPT or whatever to create the code, as long as you know what you're doing. So please try this out, and go through the architecture fully once more. Just write using your hand how the dimensions change starting from input all the way till the output. Because if you can track what happens to the dimensions, in my opinion, you know what's happening mostly in the model. So that's pretty much it. So um, yeah, so in fact, some of the assignments, since you asked about projects, the assignments that I'm posting are actually a bit project level difficulty. I can see that most of you have not submitted the assignment. In fact, I am assuming that is already difficult enough, so you can consider them as the hands-on projects. So for example, if I think it was in the Swin transformer or the one before that, I had mentioned about a different data set to be used while training, and I think people are having difficulty already. So consider the assignments that are posted themselves as mini projects that you can work to get hands-on experience, because you will have to, of course, modify the code. You won't be able to use the code directly to get any meaningful output. The second type of assignments that I'm asking to do in the dashboard is counting the number of parameters to know the size of the model, because these days we are discussing a lot about small language models. The size of the model is a very big concern, right? Even when companies try to partner, like work with us on a B2B mode, most of them want to work with small language models or smaller multimodal models. And when they say small, it means a few million parameters in many cases. So just try to make it a habit to think about the model size, even for this model, segment anything model. Ideally, you should, if you know all the layers, ideally you should be able to hand calculate the model size, right? How weights turn to probability. I think we have already covered that a lot in the initial part of the lecture. It won't be possible to have a lecture of gradient flow. It's an entirely different thing. It'll be a digression, but I'll try to make maybe a lecture video or something if I get a chance. But thank you so much. So this week's assignment is basically extending the capability of this this SAM model to have the clip-based text input also. Plus, on top of it, add the capability of the box input and mask input. And one additional thing, if you want to develop this as a small product, you can think of, see, SAM model already hosted versions you can get, or you can host it on your own server. You can even have a web-based image editing, something like that. You can think of building yourself. Like, what I mean is, click just a web interface, click on the interface to extract features, and use some other API to change colors, etc. I was discussing about this from with people. So so the major project that I'm thinking will only come at the end. It'll be only just one problem statement, because already I can see that assignments you guys are taking way longer than I expect. So I don't know what the timeline of the major project will be from your end, but please try to submit the assignments sooner. That's why I have kept the deadline open. Like, I have not defined the 1 week deadline. Initial part of the course, I was defining 1 week deadline. Then I realized that majority of the people are not able to meet the 1 week deadline. So now I have removed the deadline thing, but I expect everyone to finish all the assignments by the end of the course. So now we have a few more models to discuss. The transformer for video, we have to discuss a little bit. We have to discuss maybe one more model from vision language model I want to discuss before going into generative models like diffusion. So that's the trajectory of the rest of the course. So I might need a few more lectures, but that'll be great. This bootcamp is different from the research bootcamp. These are completely different things. So research is just meant for, there won't be any lectures, just meant for research project. If you want to check out, you can check out our page called research.visuara.ai. Just check that. But thank you, everyone. One thing, just to finally reiterate, the number of lectures you might see on the website that I have put only 14 weeks, but actual number of weeks will be much more than that. Because as I mentioned in the beginning, the transformer architecture itself, we spent at least, if I'm not wrong, 5 to 6 weeks on that. So because of that, we are offset. All the lectures are offset by 5 to 6 weeks, and some lectures like Swin required 2 lectures because coding, intuition building itself required 1 lecture. Coding was another. So I think 14 plus maybe 5 or 6 extra lectures I would need to finish everything. So just keep that in your mind. But on website currently you might see just 14, but once 15, 16th are done, I'll post it. All right, everyone. Thank you so much. I hope you enjoyed today. You learned a lot. See you next week. Bye. And advanced Happy New Year.